Volume check here. It's really not their business. Yeah, let's. Okay, we are technically 20 seconds in. All right, let us do this here. Okay, so just a quick round of announcements. Okay, I lost track of time myself. I was working on a thing in Canvas. Let's see. All right, so quiz. Today's a Tuesday. There's a quiz. So please do that online quiz today. It is a turn in the picture kind of thing. This process is actually going to take me a little longer overall because Canvas is going to make me download each picture separately from each student in order to do any grading. But that's that. Well, I'll make it work, but I hope. So I guess sorry for the timing of how long some of this stuff is going to take. But just so you know that's what's going on. Let's see, and then yeah, quiz Thursday. Please keep current with web work as much as possible. And office hours. I'm just reminding you those times. I also sent this by email yesterday just to make sure. I mean, I think everything's just a little harder. So I'm just trying to make sure everybody's staying connected. And actually, with that, I just finished it. That's what I was doing in Canvas just now. There's a survey. It is optional, but yeah, I was trying to find a way to create a survey that would be extra credit, but online, but it wouldn't allow for that. So I just please do the survey. It should be rather quick. I'm just really trying to find out how everyone's doing on a personal level first, if that's possible. Though you could certainly pass on that question. But I'm also just trying to figure out what's working and what's not working and what might need to change and that kind of thing. I wanted to do it after the first week we were back, but I've just been behind. So I was just like, this morning, I'm just going to figure it out and we're just going to do it. So just complete that survey. If you don't, I'm just sort of assuming everything is okay. The survey questions are really more built towards complaints that you have, so I would love to hear them. There's no point retaliation or anything. I just like it. They're just questions like, hey, um, you know, is the online office hours thing working for you, or have you been successful downloading the videos to watch them later if that's what you need to do because you had something come up one day where you had to drive a younger sibling to somewhere, things like that. So just trying to make sure that I mean, if you can join live, obviously that's great, but just I know that even if you join live, there's times where you can't because something comes up. And so the survey is just trying to capture like, are the other methods of getting class stuff going okay for you or not? So I think it would help me out to fill it out, especially if you have complaints so that I can adjust. So what I want to do right now is a warm up to a thing we'll do 2 slides from now, which is if you have 2 points, there's a point called x1 comma y and another point called x2 comma y. So you'll notice that both of these have the same y coordinate. That is intentional. Yeah, they share the same y coordinate. But I'd like to right now work on what would be a formula for distance between these 2 points. And I want you to just take a moment. I'm not going to wait too long so it's awkward, but I don't want to just get into it right away either. So I'm going to help you out by drawing a picture and say, okay, we've got x-axes and y-axes, but if the 2 points share the same y-coordinate, then on the y-axis they should be at the same height. So you've got like maybe a point there and a point there. So maybe, the idea behind the x sub 1 and x sub 2, the intention anyway, is that maybe these 2 points have 2 different x values. And so my question is, what would be the distance between these 2 points? Now, notice if you connect these 2 points with a straight line segment, that line segment is completely horizontal. And if this is bothering you how this is working out, then just for a moment, even though it's not in the question the way I asked it, maybe just make up a number, right? Like just pretend that this tick mark here is like a 3, I don't know, and maybe this one's a 10. I'm just making up some numbers on the spot. And figure out how long this line segment is, and see if, based on how long this line segment is, if the x-coordinate is 3 and the x-coordinate there is 10, what would be a more general thing that would happen if you erased the 3 and the 10 and just kept the x-coordinate as x1 and the other x-coordinate as x2? I'll give you about 1 minute to just think through that. Okay, the other thing I'll just maybe quickly reveal on the next slide here is I want to, you may already have a formula in mind, but I have this sort of side question of, do you have to do something different to get a valid formula if one or both of the x's happens to be negative? I think it turns out that if your formula works, and I drew everything in the first quadrant intentionally so that all the x and y values were positive, so there was no funny business. But I think if your formula works there, it should work no matter what. So what I mean is maybe something like this. Yeah, so like let's say you had the point 3 comma 8. So 3 is there, maybe 8 is here. You've got this point, and you have 10 comma 8. I should have went with this example a moment ago. And if you connect these 2 points, the distance for that, like how long is that horizontal line segment? It should be exactly 7 units long, right? So that, of course, in this specific example is, why is this pen not working here? Okay, so the distance or the length of that line segment in this example should be 10 minus 3. Okay, but if, the whole point is that this should work in general. Like more generally, even if you didn't have this picture, we should just have x2 minus x1, or rather the bigger x value minus the smaller x value. This should work even if you move both of the points 5 units to the left. I want you to imagine, for instance, let me erase this. It's a little easier to definitely point in class. I want you to imagine like there's a construction worker right where that dot is, and there's a construction worker here. And so we're looking from a bird's eye view, and these 2 construction workers are holding a steel pole that is 7 feet long, right? And if both of the people holding their ends of the pole end up walking to the left, this person walks to the left by 5 units, they'll end up over here. Sorry for that 8 in the way, but they'll end up where the x-coordinate is -2, right? If you walk 3 units this person here walks 3 units, they'll end up right on the y-axis, but then they need to, that's only 3 units, they need to walk 5 units, so a total of 2 more units. So over here at -2. Same deal, this person here walks over 5 units, and then you'll have x coordinates of -2 and 5, but in order to get the length of the pole doesn't change. It's a steel pole. It should still be 7, right? And I've seen, I think, a thing that people have done is because one x value is negative and one x value is positive, they'll think, oh, I need to do 5 plus -2 and I'll get 3. But then how did the pole become length 3? The pole length is still 7, so it should still be 5 minus -2, which would be a 5 plus 2, right? So you don't need to do anything different just because you have a negative x value. That's what I'm trying to demonstrate. I hope that's making sense here. So the whole point is, if you've got one point and another point, and both points share the same y coordinate. Now that is key here. If both points share the same y coordinate, in other words, they're drawn at the same height, then to get the distance between the 2 points, you just take the bigger x value and subtract the smaller x value. So bigger x minus smaller x. We won't go through the same experiment, but you can imagine if you had 2 points now where you have the same x coordinate, right? So just as a quick picture of this, you've got like, you've got a point here and then a point with the same x coordinate, meaning it needs to be on the same vertical line now. You can imagine that the distance formula for those two should be bigger y minus smaller y. So I want to take these two ideas, bigger x minus smaller x, and then bigger y minus smaller y. These are, by the way, go by the name of, this one's called the horizontal distance. I hope that makes sense as a name, because it's 2 points that are separated only by walking horizontally from each other. And then the other one, of course, here is called vertical distance. And the goal now is to take these two ideas and apply them. So we're going to use these two formulas, bigger x minus smaller x, as well as bigger y minus smaller y, to get this rather important formula for today's class. You may have seen this before. We're going to derive, and I don't mean differentiate. So sometimes people think of f prime as derive. So I've never used, the word derive means take old ideas and get something new. So we're going to take some old ideas and get the distance formula for 2 points in two-dimensional space. And now we've already done some warm-up versions, but in our warm-up versions, the 2 points either had the same x coordinate or the same y coordinate. I'd like to look at a situation where the 2 points don't share any coordinates. So we'll have 2 different x values, 2 different y values. We're going to use the Pythagorean theorem. So let me draw here. Just 2 generic points might look like this. So I would suggest you maybe draw that much of the picture. I'll pause for a second so you can do that. So you'll notice, unlike the other two pictures, the other two situations we drew, that there's 2 points, and the 2 points have different x values, and the 2 points have different y values. We need the distance between these 2 points, so we'll connect them with a straight line. Let's call that distance d. Now the real question I want to ask here at this point is, do you see a right triangle? Now, normally when I ask this, people start kind of indicating to me, yeah, they see a right triangle. Now it's not there directly yet, right? We've got to do some extra drawing in order to see that right triangle. So I actually see 2 right triangles. This is probably not the one you saw. If you just draw a completely horizontal line here and then a completely vertical line, maybe you saw the other one. I think it's more typical to see this one over here. If you draw complete, oh, that was not very good with the pen here, but completely horizontal line and then completely vertical line. So there it is. I advance the slide forward. It erases all my markings, and you'll see a much better computer-drawn version of this. Okay. Now what I'd like to do is I'd like to note that it's not all drawn in here. So look, this point over here at being having x1, y1 as its coordinates, we could have written x1. I kind of want to write that below, but there's these words that are in the way. x1, y1 over here. We could have labeled this if that, and then this point over here, right? This other point up in the upper right, we could label on the x-axis that we have an x2 here and a y2 over there. If you want, the point is you could label these tick marks on the x-axis and y-axis if you'd like to, but this information was already shown by having the 2 points there. The key thing being, I'd like to talk about what is this distance right here. But you'll notice that distance, since we had to create a right angle, because you'll need a right angle to use the Pythagorean theorem, right? I asked if is there a right triangle, but to create that right angle, remember we had to draw completely horizontally here, and so right there, this part that I just traced on right here, that's a horizontal distance, and we had just discussed that this horizontal distance should be bigger x value minus smaller x value. So this distance right along here should be x2 minus x1. And then right here, we have this is a completely vertical line segment. So to compute this vertical distance, it should be y2, the bigger y value minus the smaller y value. And you see them labeled over here. The y2 minus y1 should be this. And if I advance the slide forward, I think you will see a clean version of that. Okay, so we have now the 3 sides of the right triangle. One side is much easier because it's just a single letter, D. 2 other sides are a little more complicated looking, but it's just subtracting 2 numbers from each other. And now let's apply the Pythagorean theorem, right? So normally you say like a squared plus b squared equals c squared. It's just what's our a, b, and c are a little different. I also put the c squared, or I guess rather d squared, on the left side instead of the right side of the equation, but that should be fine. So stare at that, make sure that looks okay for you. Hypotenuse squared equals a non-hypotenuse squared plus the other non-hypotenuse squared. Cool, but we wanted the distance, and remember we labeled the distance d. This right here says d squared. So in order to get the distance, we should square root both sides. So we'll do that action. Let's take this equation here, square root both sides. Please keep in mind that square rooting both sides does actually introduce a plus or minus sign. This is a good reminder because there are times later on in the semester where this algebra issue comes up. But of course, in this specific situation, we're talking about distance, and a distance should never be negative, right? Like -5 for distance wouldn't make sense. So we'll just actually scratch out that plus or minus sign. I just put it there as a reminder that generally speaking, the algebra requires you to get a plus or minus sign. And then once we've done that, we should apply further reasoning to say, wait a second, because d stands for distance, we can't have a negative number. Okay, so this is the standard distance formula. It looks funky as written. You can't simplify this any further. What I mean is people's attempts to simplify this further by distributing, in quotes, a square root symbol and trying to cancel that with the squares is algebra that does not work. That's an algebra mistake. So this is as simple as the formula gets. I wish it simplified further, but it doesn't. The point is, I think when just presented the formula on its own, people just think, oh, I'll memorize it just fine, and they don't. I've tried it in algebra class before. I think it's important to see where all the pieces come from. So you see that the formula has squares twice, and that's because in the Pythagorean theorem you've got like an a squared and a b squared. You'll also see there's a square root sign, and the whole reason there's a square root sign is because originally in the Pythagorean theorem there was a c squared, but we didn't want c squared. We wanted c, and every time I say c, you get that I mean d here, right? So since we wanted the distance, we had to square root. So seeing where all the pieces come from, I think really helps in the process. I've seen people, instead of a plus sign down here, and instead of minus signs in those 2 spots that are circled, I've seen people switch the things around. So where the 2 minus signs are, I've seen 2 plus signs instead. I mean, you got to really think about the processes that we've just talked about here. This plus sign circled right there is because in the Pythagorean theorem, you say a squared plus b squared. The minus signs come from the experiment we just did a moment ago about how do we get vertical distance and horizontal distance. Okay, so there's this distance formula right down here. We are going to apply this in an upcoming example optimization problem, but I have one other thing I want to say first before we start that problem. I just want to pause, see if we're doing okay, see if there's any questions about how we got this distance formula that's boxed at the bottom first. So I'll just maybe wait for a second, see if there's anything that comes up for people. Okay, so I'm not seeing anything. And sorry for the awkwardly long pauses. I just know from having experimented with some colleagues during spring break using this software that I say something and it takes about 5 seconds later when you actually end up hearing it. So I don't want to start talking right away because then I'll interrupt your question accidentally. Okay, so we're going to try this experiment, which sounds a little strange. Normally, I have people with index cards, like somebody with an index card that says 25 and somebody with an index card that says 81, and I ask them to actually stand in front of the room to do this. But we're just going to do this on paper here, I guess, right? So I'd like to take this list of numbers. We're going to, step one, put the numbers in order. Then step two, we're going to take the square root of each of the numbers. And then after, we're going to take the square root of numbers and put those numbers in order. And then what do we notice? Because this experiment is not meant to be busy work. There's some really important idea that's going to save us a lot of time in the next optimization problem if we get the key point of this experiment here. So let's put these numbers in order, smallest to largest. So 1 first, okay, and then 4, and then 9 over there, and then 16, and then 25. Sorry, my pen is not doing well today. I might have to replace the battery later. 36, and then 49, 64, yeah. 81, 100, 121, and 144. Okay, so the numbers here are in order, and now, so step one, check. Step two, take the square root of each of the numbers. I'll just write it right below. So square root of 1 is 1 because 1 squared is 1. Square root of 4 is 2 because 2 squared is 4. So sorry for saying that, but the first one, I know you know the square root of 4 is 2, but sometimes people get really choked up on the square root of 1 and end up calling it 1/2 or something like that. But it's this thingy squared is that thingy, just like this thingy squared is that thingy, right? So yeah, I'm going to have to, I thought my erase feature would work. I'll just have to do that. Sorry. Okay, so 1, 2, 3. Square root of 16 is 4. I think you see what's happening here with the numbers that were chosen anyway in the list to begin with. Cool. Take the square root of each of the numbers. Now take the square rooted numbers, meaning let's look at this new list and let's put them in order. What do you notice? What do we have to do to put these in order? We don't have to do anything, right? So the thing to notice here, these numbers are already in order. So since the numbers here were already put in order in step one, even though the actual numbers we were meant to sort in step 3 were different, they were already in order. What are we supposed to get from this? The key fact we're supposed to get from this is if you have numbers that are already in order, then if you square root the numbers, that's not going to end up changing the order. Or so that'll be true if you square root or if you do the reverse process of squaring. So if you've got a bunch of numbers that are already in order and then you square all the numbers, the new resulting numbers should still be in order. Now, these kinds of processes don't always work out, right? Like just because you've got some things in order, you do some process and then you end up mutilating or changing the numbers. That doesn't mean that your new list of numbers is always going to be in order. But for square rooting or squaring, that always works out. How's that going to apply and help us out? For what we're about to do, to find the x value that makes y small or k small or whatever letter, instead of y, to find the x that makes y small, if it's more convenient, then you should just find the x which makes y squared small instead. Sometimes, talking about y being small, you'd rather talk about y squared being small. Sometimes it just makes the calculus that you need to do go a lot more smoothly. So we're going to see this idea show up in the optimization problem we're about to work on. We're also going to see the idea we just saw a moment ago, which was the distance formula in the problem we're going to work on. So here's the question. Here's the optimization problem. Find the point on the curve y equals root x, which is closest to the point 16, 0. So just this is a graph that I want you to know what it looks like, but I will just quickly draw for you that this is a sideways half parabola that looks like that. Okay, it's the standard parabola, but kind of turned on its side and only half of it because we only have plus square root. There's not a plus or minus sign. The point 16,0 would be like somewhere over here, right? So that's, first of all, just a general version of the picture. And the point is that if I just extend this quite a bit, it's never decreasing, so it's increasing just ever more slowly. Like this point over here is probably too far away. Like this point over here is probably too far away. The point we're probably looking for is maybe like somewhere over there, roughly speaking. So we're asked to find the point on this curve that is closest to this point down there. Okay, so the quantities I'd like to bring up here for x will stand for the x coordinate of the point on the parabola. Y will be the y coordinate of the point on the parabola. And then d will be the distance between the point on, so if little x and little y stand for the x and y coordinate of the point on the parabola, then x comma y is a point, and then 16 comma 0 is the point that was provided up there. And we so then little d will stand for the distance between these 2 points. Now I hope you're seeing why we needed to talk about the distance formula, or rather review it. Excuse me here just a sec. Okay. Yeah. All right. So now the thing that we need to do is take a look at this word closest. This is supposed to give us what our objective is, and our goal should be to minimize. Let's write this over here, right? Our goal should be to minimize d. Now we're going to cross this out in a second. It's fine if you would like to minimize d, but the thing is, we just saw a moment ago that d, the distance formula, has a square root symbol in it, and so it'd be much nicer if we didn't have to deal with that square root symbol. So instead of minimizing d, here's that other idea we saw. It might be more convenient for us if we minimize the square of d instead. So here's what I've got is let's let s end up being the square of the distance, or in other words, d squared. And we'll minimize s instead of d because the x value that minimizes d is going to be the same x value that minimizes s. That was the key point I wanted to, so that was the whole thing about taking a bunch of numbers and sorting them and squaring them or square rooting them. After that process occurs, you'll still have things in the same order. If you'd like to click on the picture, I already drew it for you on screen, but if you'd like to click to see a picture later, you can do that. Let's write down then some equations that we've got that relate the quantities together. So first of all, you can relate d, x, and y together using the distance formula, because d here literally stands for, we said that it should be the distance between this point and that point. So apply the distance formula that we just reviewed, and you should get that. S, at least in words, was the square of the distance. So then if we put this in notation language, then s equals d squared. And then finally, if you have a point, so x and y are the x and y coordinate of a point on the sideways half parabola. So if you have a point on that parabola, has to satisfy this equation up here, y equals root x. Otherwise, it's not on the parabola. So this equation that was provided in the question helps relate together two quantities, namely the x and y coordinates. So it's another equation that relates together 2 out of the 4 quantities. So we have this equation that's got 3 out of the 4 quantities, d, x, and y. We've got this one that has 2 out of the 4 quantities, s and d. We have this equation that has 2 out of the 4 quantities, x and y. Okay, so we now see that we're going to try to minimize s. So we should get s solved for by itself. We have s equals d squared, so that's going to be helpful. It might actually help us to first take, and here's where you've got to look at your kind of several equations. There's many variables. There's 4 variables, and I know that feels like a lot, but you'll see, like in an example tomorrow, there'll be even more variables than that. I think we're looking at a 6 variable version tomorrow. So at least there's only 4, which is still a lot. I'm going to start from that d equals radical, that equation, and I'm going to square both sides. But actually, before doing that, let me just note that the -0 here, I put it there so that you could see a reminder of what's going on with the, let me step back so we can just focus on one thing at a time here. So I replaced actually first the y with root x. Let me comment, there's a lot of different ways to do this that all work. Okay, so I replaced y with root x because of this equation right there. So what we have down here is another way of writing d. But you'll notice this version of writing d had x's and y's, and this version down here of writing d to the right of the equal sign only has x's. So that's a good start. In addition, so I hope that clears up going from here to there. In addition, we don't need to write the minus 0. Right? So it was there just like to make it really look like the distance formula so we could see where everything came from. But if that minus 0 isn't there, take a look. Now we've got a square root symbol and a square that do cancel each other out. This bigger square root symbol doesn't because it doesn't distribute. But here we don't have anything else in the parentheses. The minus 0 isn't there anymore. So the root and the square undo each other and we're just left with an x there. Okay, so root x squared simplified to that x right there. Everything otherwise is still inside the radical. The radical does not distribute. However, so that we don't have to deal with this radical, let's square both sides. So if you square the left side, you get d squared. If you square the right side, you get rid of the square root sign. So I'm not distributing the square root symbol here. That does not make sense in algebra. I'm squaring both sides, which does make sense. So square the right side, there's no more radical sign. Square the left side, we'll just write that as d squared, or a more convenient way to write d squared is we can just replace it with an s. So all that happened now is the left side, instead of saying d squared, is replaced with s. So we have s is equal to quantity x minus 16 squared plus x. Take a look at this. S is the thing that we said we're going to minimize. We're saying s is our objective. And now, to the right of the equal sign, there's only one variable over here. That's good, right? So we can differentiate this. Now, your call. When taking the derivative, you have some options. You can FOIL this out and then differentiate s, or you can just differentiate kind of straight away, but you have to use the chain rule. Both are about the same amount of work. So I think as just a chance to review the chain rule, I'm going to do it that way. Yeah, so I made the comment that you could FOIL out x minus 16 quantity squared and then differentiate that way. It works, but the chain rule way here is, let's see, exterior function of x squared. So there's the 2, and this is to the first power of the inside stuff, so x minus 16. But then there's this times 1 that I wrote here as a reminder that you've got to differentiate the inside thing, and the derivative of x minus 16 is a 1. So that's what that times 1 is about. Then the plus sign is copied from up here, and then you have to differentiate x, and you'll get a 1 when that happens. So this is how the derivative looks if you use the chain rule. You'll get a slightly different looking answer if you FOIL and differentiate, but it is the same thing actually if you look at the algebra. So look, we don't need to write this times 1. Of course, I just wrote it there as a reminder that there's this second part of the chain rule, but we should do now the usual things, right? We took a derivative. In other words, this is a formula for the slope of the and we should set this equal to 0 because we're just trying to see where there's a peak or a valley. So if I left out the times 1, but if we set this equal to 0, you should subtract 1 on both sides and then divide by 2 on both sides. So you have x minus 16 equals a negative a half. And then to solve for x, you need to add 16 to both sides. So that 16, by the way, is 32 halves. So 32 halves minus the 1 half that was there is 31 halves. I'll pause here, see if we're doing okay. Okay, so this slide so far has shown quite a lot of work. I'm going to keep the quantities up here, and any of the relevant equations, I'm going to, in the next slide, cut out some of the work so that we have room to talk about some of the next steps. So in this section that says before, it's just really copy pasting from what we had earlier. The language here in this line is slightly different, but it does summarize what we just did. After setting s prime of x equal to 0, we got that x equals 31 over 2. So that value of x seems special. Like that's going to do something for us, right? That's a critical number is actually the language. Now the real question is what happens at that x value? Is that a place where s is big or where s is small? In other words, in more technical language, does s have a local minimum there or a local maximum there? We're hoping that to see a local minimum because we want a closest point. We want s to be small, right? We're trying to minimize s. So we'll see what happens here. You can apply the first derivative test if you want, but I think it's actually going to be more convenient to apply the second derivative test. So in order to do that, I looked at this s prime that was up here, and I said, I don't want to use the product rule. Let me just write this nicer in algebra first. So this is not a derivative yet. It's just if you distribute the 2, ignore the times 1, so 2x minus 32, but oh yeah, but there's a plus 1. So that's why this says 2x minus 31. It was really a 2x minus 32 plus 1, but you've got to simplify the constant. Now that looks super nice to differentiate. So s double prime is, well, differentiate 2x to a 2, and the derivative of negative 31, that's a constant, so the derivative there is 0. We need to, just to illustrate the point though, this 2 here is actually the function. Like normally when you differentiate you still have x's. What we need to do now, just to make the point and make it consistent with what we've done in the past, we should take this special value of x and plug this into the second derivative, meaning everywhere that we see an x we should replace with a 31 over 2. And I really mean that. Replace every x with 31 over 2. So s double prime of 31 over 2. The only place to replace an x was right here. Sometimes people overthink this and replace this 2 with a 31 over 2 or something like that. Don't do that. Just literally replace every x. The only one is right there. There's no x to the right of the equal sign. That's fine. So we end up getting the number 2. Since the second derivative is a positive number, s has a local minimum. We're okay with that? The second derivative is positive, so there's a local minimum, right? If that sounds strange, please remember that the second derivative being positive means that, so s double prime positive is the thing that translates into s is concave up. And concave up pictures are going to have a local minimum right at the spot where the derivative is 0 or right where the slope is 0. Okay, so we've got a local minimum at this x value. This means that this x value, 31 halves, is the x value that is going to make s small. And if it makes s small, it also makes d small. So that was that whole experiment of taking these numbers, and the order of the numbers, which number is smallest, in other words, doesn't change if you square the numbers or if you square root the numbers. It was just a way to not have to deal with the square root symbol, because if you wanted to differentiate d the way it's originally written, there's a square root and stuff inside, you'd have to apply the chain rule. It works out, it's just way messier, that's all. Okay, so we know that this value of x makes s small, so therefore it makes d small, right? So since s is equal to d squared, the x value that makes s the smallest also makes d the smallest. And we can go back and now think about answering the question. The question said find the point on the curve. So we know the x coordinate of the point. We know that the x value we need, that special x value, is 31 over 2. But a point has an x coordinate and a y coordinate. So we need the y coordinate, and that's where this equation, I meant to put in this list, but I didn't to save space because it's already up there. To get the y coordinate of the point, since we know the x value, the y value is found using this equation. So from x equals 31 over 2, and also knowing that y is equal to root x, we can plug in this x value into this spot right there and see that the y coordinate of the point we need is root 31 over 2. And so then all in all, the x value from up here and then the y value that we just got should be stuck inside parentheses with a comma between. That's how we use our point notation, to say that that is the point that is on this curve, that is on this sideways half parabola, that is in fact closest to the point 16, 0. Now we're actually done with the question at this point. Should have had a happy face here. I will just point out though that if the question had been different, if it didn't say find the point on the curve, if it had instead asked what is the distance between the closest point on the curve and the point 16, 0, then you can compute the distance as well, because the distance, so that's why I'm doing this to illustrate there's a difference between s and d, right? So it's important to know what variable means what, which is why it's it's super important to write out things like this. Sometimes people just try to attack these questions without even writing down what their variables mean, and that gets them into trouble. I've seen it happen in office hours a lot. Um, so knowing that d is the thing that stands for distance, we just happen to minimize s instead of d. To get the actual distance, well, d is written over here, and now that we know both x and y, I just plug those in, and now this is a number that could be typed into a calculator. Not that we're going to do it, I'm just saying that there's no variables there. That number right there is literally the exact distance between the 2 points. Okay, you'll find that as you do some of these problems, when it's time to answer the original question, go back to look. You're doing all this optimization process, and ask at the end. Okay, I've got to answer what the question was. Which variable addresses the question? And if you don't already have that variable equals a number, you probably eliminated that variable. And so it meant you probably already solved that variable to do a substitution. So go back through your work. I promise like 100% of the time you've already solved for that variable. So then use that equation where you've solved for that variable. It will, if you need the value of a certain variable at the end of the process, you already solved for it. Or you could rework out the work. Sometimes I see people do that. The big story here, again, of course, is that we are using our methods for finding local mins and maxes. You do need to get to the point where you have the objective on one side, and then on the other side of the equal sign you have only one variable before differentiating. So since we did talk about distance, I'd like you to look at questions 13 and 14 on the sheet. I will pull them up here. If you get stuck, feel free to ask a question. Let me zoom in to 13 and 14 are these. There we go. So I'm just going to kind of wait around here, see if you've got a question. You can unmute a mic. You can just type in the chat. Anything in the chat is not going to end up in the recording because I intentionally pushed my chat window to the other screen, and I'm only recording the other screen. So. And yeah, really, really try these. I know it's just easy to just like walk out of the classroom door. I've seen people do this if we were meeting in person, but 13 and 14 are really close to the thing that we just did. They're very, very similar. I think it'd be really good to retry this approach, or as you work on it, ask me a question, or if you get stuck and you want other resources, you could, of course, look at the slides as but one way or another, I would really suggest, while this is fresh in your memory, trying at least one out of question 13 or 14 right now. Better to do it now than just get stuck and then have to come to office hours later for it, because there are web work questions that look like this too. What are the ah? I see this question of what are the answers for each. Let me just pull up another file here, and I actually that's a good reminder. I've been meaning to upload. Excuse me, I muted myself accidentally. Upload some solutions. Let me just go find a file and at least state final answers, and then I want you all to. I didn't post them right away because I did want people to be working on things. So let me just go find the file. Give me just a moment here. Let's see. Because in 4 minutes, I might just have enough time to work out both super fast. But instead of doing that, I'm gonna. Oh, here we go. Questions 13 and 14. Yeah, and I will post this PDF that you're seeing right here. So question 13. I I'm gonna zoom in so that you can see it on screen. I hope. Sorry, I did use a thin marker. This question 14. The closest point I got was 2 comma 2, and I wrote down over here the distance looks maybe a little funky, but I hope that helps. And then question 14 on page 14 here. I got for the x coordinate negative 17 squared times 2 over 2 plus 17 squared times 2. And then here's my x and y coordinates. They look a little messy as written, but I hope that kind of helps. I mean, what I'm showing in this PDF are non-calculator solutions for this. So would it help if I post these? Yeah, okay. So I will do that. And again, the idea, you get what I mean. Like this was sort of like oh, people should work on these on their own. So the thing is, this is, as maybe you can see it kind of up here, this is a single PDF file, 14 pages long, one PDF page per question that's in the problem sheet. And so it's super tempting, I think, to just like do one problem and then look at the key and then, don't just look at the keys. You get what I'm trying to say. You gotta, I mean, you can do whatever you want in the end, but you try to be as responsible as possible with this. You gotta practice. So I will post this. How about right after I've got to get set up and erase things and all these things for the next section. So at 10 o'clock, I will have this uploaded in Canvas. I hope that works. I guess since we just have 2 minutes, I'll just do a quick round of reminder announcements, especially because it is a Tuesday. Oh yeah, and I just, in case you joined us a little late here, I did just create a survey. Like, I mean, just like 2 minutes before our class started, I finished writing the survey. It's just meant to kind of collect any kind of complaints you have about any of the process here. I mean, I can't do everything, but I'm things are actually busier for me than they were in the past because of being online. But if something's like really not working for a lot of people, I need to fix it, and this is an opportunity for you to just let me know. No retaliation against your grade or anything like that. Just let me know what's not working. Like I'm trying to download videos and this isn't working. That came up for a couple people, for instance, so I started posting the videos on YouTube as well. But like I just want to know what works and what doesn't work. So if you would fill that out, that would help me out. The other key thing, of course, is since it is a Tuesday, there's an online quiz. Be sure to do that. That's maybe the most time-sensitive announcement to make. And I will see you either for office hours or for class tomorrow, and we'll do more optimization tomorrow. Again, the deal is I will start class with an optimization problem, and then I'll ask you to take the remainder of the time to work on optimization. Tomorrow, I think, is the most challenging of the problems we'll look at, but we had to build up like this. All right, see you tomorrow.